we're going to look at another way of finding volumes. Cylindrical shells. What we do with this one, instead of taking a slice perpendicular to the axis, we take it parallel to the axis. So what happens, let's draw up random curve. There's random curve. And we're going between A and B again. I'm going to rotate around the y-axis, sorry, not the x-axis here. So instead of going what would have been horizontal, we're now going vertical. Now, the advantage of that in this sort of question, even in this random one when I put in, imagine if I had done discs on this, then I would have had to actually have done two different ones because the boundaries change. Because if you're going horizontal, you'll notice I'll go, oh well, blue curve to red curve, blue curve to red curve. But once I get past the bottom of the red curve, I'm going, oh, blue to blue. So it changes. So I've really got two different situations. So the advantage of doing this one, top minus bottom, is consistent for the whole region. So I don't have to split it up into two. When we rotate that, we get what we call a cylindrical shell. So we've got like a cylinder with a hole in it. And it becomes a bit like, what do they call them, babushka dolls? You know those Russian dolls where you have one inside the other, And that's sort of what we got here. If you were to add up all these cylindrical shells, you're putting one shell inside the other, and you get your solid. You still get the same solid. Now, I find it easier to unwrap the cylinder and think of it as a rectangular prism rather than a cylinder. Now, yes, theoretically, these heights are not going to be the same because of the curve, but remember, we're going to be dealing with delta x approaching 0. So if it's approaching 0, the difference in the height is negligible. So it's okay to treat this all as if it's constant. So if it is a rectangle, my thickness is delta x, the height would be the y value, but thickness is x, so I want it in terms of x, so I'd have to rearrange that. Okay, I want whatever function x is. The base of my rectangle there would be the circumference of the circle, because that's what I've unwrapped. So it would be 2 pi times the radius, and the radius in this case would be the x value. So 2 pi x. So my area function becomes 2 pi x times whatever function x is. So there's my area. Now from there, that point on, it becomes the same process, because all we're doing is adding up all the slices. It's still the same idea. So I want to find that element of volume. So to make it a volume, I'll multiply it by the thickness, delta x, and then we can say, righto, I'm going to sum up all of these thicknesses, and I'm going from A to B. And then that becomes our integral. Well, 2 pi is a constant. I can bring that out of the front, and we get x function x. Now, you see some textbooks actually just quote a formula, 2 pi xy, right? Because function x is the y value if you think about it. Don't do that. Right? Again, they want to see where it comes from. They don't want quoting 2 pi xy, I guess, is equivalent to, in the disk one, just quoting the 2-unit formula and going integral of pi times y squared dx. That's not what this is about. We want to build this. So don't quote that. We want to build it up. Let's try the same question from yesterday, but we'll now do it with cylindrical shells. So the volume is our upside down parabola, and we were rotating it about the x-axis. So instead of doing, yesterday we took a vertical slice, we're now going to take a horizontal slice and go parallel. So the thickness will be in terms of y. So if I rotate that, I would get my cylinder, which I'm going to unwrap and make a rectangular prism. Thickness is delta y. Now, the height of that is going to be twice the x value, because we've got symmetry either side there. So down the bottom I've got 2x, but I want that in terms of y. So when I rearrange this to get to x the subject, now you're looking at it thinking, hang on, if x is the subject, surely, and you notice I've used index form, but surely it's actually plus or minus the square root. And it is. You're dead right. Because what am I looking at here? I'm a parabola, axis of symmetry, plus the square root minus the square root. Just like in the quadratic formula, you have minus b on 2a plus or minus. But because of symmetry of a parabola, this x value, the magnitude of it, the size of it, will be the same as that negative amount there. So it is okay to just go twice the... I'm going to use the positive one because it just makes more sense to work with the positives rather than the negatives. Okay, so 2x, so we're going to have two lots of 4 minus y to the power of a half. Now the circumference will be 2 pi, and in this case it will be whatever the y value is. So the area of that rectangle becomes 2 pi y times 4 minus y to the power of a half. So my volume, and also tidying up the algebra in my area function, is 4 pi y, 4 minus y to the power of a half. So we want to sum that, and we're going from 0 to 4. So there's my sum. There's my integral. Okay. Now, remember, I'm using this as an example to show we will get the same answer. When we look at the integration, if you remember the integration from yesterday, it was quite simple. We've ended up with something a little bit more complicated here. So in this case, it's probably not a good question to do the cylindrical shells way. But as I say, for the sake of showing, hey, look, we get the same answer. But one thing I do notice, I've got lucky here. Look, 0 to 4. And remember from integration, we've got that neat little formula that says, hey, integral of 0 to a of function x minus a. So I'm going to use that to make life a little bit easier. So everywhere I see y, I'm going to replace it with 4 minus y. That is easier to integrate because I can expand those parentheses out, and now I've got one where I can just add 1 to the power over the power. Subbing in 4, subbing in 0, and sure enough, we get the same answer as we did yesterday. Let's have a look at another one. This one's nice. Volume generated when x squared plus y squared equals 4, which is of course our circle, but we're going to go around the line x equals 4. We're going to end up with a donut. So how do we find the volume of a donut? Okay. Well, I'm going to go parallel to the axis. So there's my thickness. I'm going to rotate that around, and we'll end up, as I say, with a donut. Here's my attempt to try and draw the donut. Use your imaginations. Okay, so we've got a donut if we were to rotate the whole thing. But what we're more interested in is that cylindrical shell. Oh, by the way, I'm calling it a donut. Technical maths name, torus. Unwrap it. Rectangular prism. The thickness is in terms of x. So all right, let's have a look at all the different features. We know the height of it. Well, again, we've got twice the y value because we've got a bit above, bit below, but we've got symmetry there. I want that in terms of x. So if I rewrite my function, I'll get 2 lots of the square root of 4 minus x squared. The radius in this case, okay, we're rotating around 4. It'll be minus the x value. 4, so we're going 2 pi the radius, 2 pi 4 minus the x-axis, minus the x-axis, minus the x value. So you're drawing from the axis to the slice. Axis to the slice, 4 minus whatever the x value is at that slice. Alright, so let's put it together. Length times breadth. Tidy that up. Delta V, there's my element of volume. Here's my summing them all up. Now, let's integrate. Notice I have not gone twice 0 to 2 because I don't have symmetry with this one. Look back at the picture. Right? In this case, because we're integrating along the x-axis, it is not symmetrical for this one. Those shapes will be different when we rotate. So that one, we keep minus 2 to 2. I'm going to break that up into 2 integrals though. 4 times the square root of 4 minus x squared, and x times the 4 minus x squared, because something beautiful happens. Okay, if you remember this is where all those techniques we looked at in integration now come in handy. Okay, got to factorise there, 16 pi. Have a look at this, square root of 4 minus x squared going from minus 2 to 2. It's a semicircle, half pi r squared. But what's even better, look at the second one. Minus 2 to 2 of x times square root of 4 minus x squared. Hang on, x is an odd function. The square root of 4 minus x squared is an even function. Odd times even is odd. Integral from minus 2 to 2 of an odd function, 0. I don't have to touch that integral, it's just 0. So I can go, yep, semicircle, pi r squared, or half a pi r squared, and over there I can say, oh, well, I've got an odd function, 0. And there's my answer, 32 pi squared. So I don't actually have to do any integrating at all with this one if I make use of our techniques of integration. So if you spot those sorts of things, gosh, that can save you a bit of time. Alrighty, that'll do for our example on cylindrical shells. Again, some from the Cambridge, and then a couple out of Patel to have a look at.